The XB-70 Valkyrie was conceived in the turbulent atmosphere of the early Cold War, when the United States sought ways to maintain an unassailable nuclear strike capability against the Soviet Union. In the late 1940s and early 1950s, Strategic Air Command relied on propeller-driven bombers such as the B-36 Peacemaker and then the jet-powered B-47 Stratojet. Yet as Soviet air defenses grew more sophisticated, the American leadership demanded a new platform that could outpace and outfly any interceptor or missile then envisioned. The ideal solution appeared to be a Mach 3 bomber, one that could cruise at altitudes above 70,000 feet, immune to both fighters and surface-to-air missiles. The Air Force's early studies, grouped under the Weapon System 110 program, sought to define such a bomber. By the mid-1950s, the concept had coalesced into a massive delta-wing aircraft powered by 6 engines using advanced materials and aerodynamics. The North American Aviation Company, which had already designed the P-51 Mustang and the F-86 Sabre, secured the contract. Led by engineers such as Harrison Storms, the company envisioned an aircraft unlike any seen before. 185 feet long, 10,000 pounds at takeoff, with a crew of 4. The strategic rationale was simple. At the time, intercontinental ballistic missiles were still unreliable, and the United States required manned bombers to serve as its nuclear deterrent. The XB-70 would carry a payload of nuclear weapons deep into Soviet territory, relying on speed and altitude rather than stealth. If successful, it would become the backbone of Strategic Air Command well into the 1970s and beyond. Designing such an aircraft was an extraordinary challenge. The skin would heat to over 300 degrees Fahrenheit due to air friction at Mach 3, requiring stainless steel honeycomb panels and titanium structures. Conventional aluminum could not withstand the thermal stresses. Engineers devised a complex manufacturing process, bonding thin sheets of stainless steel into lightweight but strong components. Equally demanding was propulsion. The aircraft required 6 General Electric YJ-93 turbojet engines, each producing 30,000 pounds of thrust with afterburner. They were among the most powerful jet engines ever built for a bomber. Aerodynamically, the Valkyrie introduced radical features. Its immense delta wing incorporated movable tips that could droop downward by 25 degrees at high speed. This innovation generated additional lift through compression lift, exploiting shock waves under the fuselage. It was a clever solution that turned a perceived aerodynamic problem into an asset, improving stability and efficiency at supersonic speeds. The Air Force and North American promised an aircraft that would cruise at Mach 3 for thousands of miles, reaching targets across the Soviet Union before defenses could react. In theory, Soviet interceptors would not be able to reach such altitudes or speeds, and surface-to-air missile technology was still in its infancy. To many in Washington and at Wright-Patterson Air Force Base, the Valkyrie seemed the logical successor to the B-52 Stratofortress. But from the beginning, the program attracted criticism. The projected costs were astronomical, with estimates exceeding $10 billion in 1950s dollars. Critics argued that ICBMs, once perfected, would deliver nuclear warheads more cheaply and reliably. Others pointed to the rapid development of Soviet missile systems such as the SA-2 guideline, which shot down the U-2 spy plane in 1960. If such missiles could hit a reconnaissance aircraft at high altitude, could they not also threaten a massive bomber no matter how fast? Despite doubts, the Valkyrie pressed forward. Its sheer ambition captured the imagination of both engineers and the public, representing the pinnacle of Cold War technological rivalry. To some, it embodied America's determination to dominate the skies through innovation. To others, it was already outdated before its first flight, a monument to strategic uncertainty. In either case, the XB-70 was underway, and its story would become one of the most spectacular yet controversial episodes in aviation history. The Valkyrie program advanced into its prototype and testing phase with high expectations, yet each stage revealed the enormous complexities of turning such an ambitious vision into reality. By the late 1950s, North American aviation had begun assembling the first airframes at its Palmdale, California facility. The aircraft that emerged, designated XB-70A, looked futuristic even by contemporary standards. A sleek, needle-nosed fuselage stretching nearly 190 feet, enormous delta wings with foldable tips, and 6 massive engines buried in the underside of the fuselage. It was the largest supersonic aircraft ever attempted, and its appearance reflected both cutting-edge design and formidable technical hurdles. Ground tests exposed the scale of these challenges. The stainless steel honeycomb skin panels proved extremely difficult to fabricate, with high rejection rates during manufacturing. Welding techniques had to be rethought as conventional methods produced cracks or weaknesses under heat. Every subsystem required re-engineering for sustained supersonic flight. Fuel pumps had to function at temperatures far above those of normal aircraft. Lubricants needed to resist breakdown at extreme heat, and cockpit glazing had to be redesigned with multiple layers to protect the crew from both aerodynamic heating and radiation from nuclear flashes. The engines themselves, the General Electric YJ-93s, represented one of the most advanced propulsion efforts of the era. Capable of producing immense thrust, they were designed to operate continuously at high Mach speeds without catastrophic overheating. Integrating these engines into the Valkyrie's structure required vast inlets that could manage supersonic airflow, slowing it down before entering the compressors. Engineers spent years refining variable geometry intake ramps and bypass systems to prevent surges and flameouts. After years of development delays, the first XB-70A prototype was finally rolled out in May 1964. The sight of the Valkyrie on the tarmac underscored both the scale of American aerospace ambition and the looming uncertainty about its future. At nearly twice the size of a B-58 Hustler and dwarfing most contemporary fighters, the Valkyrie embodied the concept of a strategic bomber as a technological marvel rather than merely a weapon. The maiden flight took place on 21 September 1964, with test pilots Al White and Joe Cotton at the controls. Lasting just over an hour, the flight was cautious, limited to subsonic speeds, but it demonstrated that the Valkyrie could be safely handled despite its immense size. Subsequent flights gradually expanded the envelope, testing stability, control responses, and system reliability. By October 1965, the XB-70 had exceeded Mach 1, and by May 1966, it reached its intended performance of Mach 3 at 70,000 feet, confirming the aerodynamic theories of compression lift and wingtip droop. Yet success came at a cost. Each supersonic flight revealed stresses on the airframe, with skin panels showing warping and rivets loosening under the intense heating cycles. At Mach 3, the nose of the aircraft reached nearly 600 degrees Fahrenheit, hotter than many jet engines of the era. Engineers monitored every flight for material fatigue and sought to patch weaknesses, but doubts grew about whether the Valkyrie could ever operate as a frontline bomber enduring hundreds of high-speed sorties. Testing also revealed operational limitations. Fuel consumption was massive, and range estimates proved overly optimistic. Even with aerial refueling, the XB-70's endurance remained a concern. Moreover, by the mid-1960s, Soviet air defense technology had advanced faster than anticipated. High-altitude supersonic bombers, once considered invulnerable, were now threatened by modern surface-to-air missiles and interceptor aircraft designed specifically to counter such intruders. Despite these realities, the Valkyrie demonstrated extraordinary flying qualities. Pilots praised its stability at Mach 3, describing it as surprisingly smooth and controllable. Its massive wings provided a solid platform, and its speed gave an impression of untouchable power. For the aerospace community, the XB-70 was a triumph of engineering, even if its military justification was becoming increasingly tenuous. By the end of its test program's first phase, 2 XB-70A prototypes had accumulated hundreds of hours in the air, gathering valuable data. Though originally planned as the precursor to a fleet of production B-70 bombers, it was already clear that the Valkyrie's destiny lay elsewhere. The bomber role that had inspired its creation was fading into obsolescence, replaced by a new strategic balance dominated by intercontinental ballistic missiles. Still, the prototypes pressed ahead, offering insights into high-speed aerodynamics and material science that would influence aerospace design for decades to come. As the XB-70 transitioned from experimental prototype to consideration for operational service, the United States Air Force faced a growing dilemma. Originally envisioned as the crown jewel of Strategic Air Command, the Valkyrie was supposed to replace the B-52 Stratofortress and give the United States an invulnerable strike platform capable of outrunning Soviet defenses. By the early 1960s, however, the strategic context had shifted dramatically. The development of intercontinental ballistic missiles promised faster, cheaper, and arguably more reliable nuclear delivery than any manned aircraft. The very logic of building a Mach 3 bomber was being undermined before the Valkyrie had even proven itself in testing. When the XB-70 program was first launched, the Air Force planned for more than 100 operational bombers. These would form the backbone of America's deterrent force well into the 1970s. Yet by the time the prototypes flew, that number had been reduced repeatedly, first to 62, then to 12, and eventually canceled altogether as an operational bomber program. Congressional hearings, Pentagon budget reviews, and inter-service rivalries all played a role in eroding support. Secretary of Defense Robert McNamara in particular became a vocal critic of the project. He argued that ICBMs and the emerging fleet of Polaris submarines rendered the B-70 unnecessary. In his view, the Valkyrie was an outdated concept whose cost could not be justified in the age of missile deterrence. Even so, the Air Force resisted. Many within Strategic Air Command continued to advocate for the Valkyrie, believing that manned bombers offered flexibility missiles could not. Unlike an ICBM, which once launched could not be recalled, a bomber could be sent aloft during a crisis, held in reserve, or redirected to another target. This flexibility was particularly attractive during the volatile years of the early 1960s, when superpower tensions flared repeatedly. Advocates also emphasized that bombers carried much larger payloads and could adapt to conventional as well as nuclear roles, giving them a versatility absent in missile forces. The Valkyrie's test results further bolstered the case. By mid-1966, it had demonstrated sustained flight at Mach 3 and altitudes exceeding 70,000 feet. No other bomber in the world approached such performance. To the pilots who flew it, the XB-70 seemed like a glimpse of the future. Its speed and altitude placed it beyond the reach of almost all existing Soviet aircraft, and its design innovations promised capabilities that, on paper, justified its enormous costs. Nevertheless, operational integration never occurred. No squadrons were formed around the Valkyrie, and no bases were equipped to support its unique maintenance requirements. Instead, the two prototypes were used primarily as research aircraft, gathering data on aerodynamics, heating, and propulsion. For many in the Air Force, this was a bitter disappointment. The bomber that was supposed to redefine strategic aviation was reduced to an experimental testbed. At the same time, developments in Soviet air defense highlighted the vulnerabilities of the Valkyrie. The downing of Gary Powers' U-2 spy plane in 1960 by an SA-2 missile had already shown that high-altitude aircraft were no longer immune. By the mid-1960s, improved surface-to-air missiles and new interceptor designs suggested that even a Mach 3 bomber would not remain untouchable for long. As costs rose and doubts grew, the argument for deploying the XB-70 became harder to sustain. Still, the aircraft's very existence influenced global perceptions. The Soviet Union closely monitored the Valkyrie, interpreting it as evidence of American willingness to pursue advanced weapons regardless of cost. Soviet propaganda often portrayed the XB-70 as a symbol of aggressive U.S. military planning, while their own designers were pressed to develop countermeasures. Though it never entered operational service, the Valkyrie nevertheless shaped Cold War strategy by forcing adversaries to prepare for a threat that, in the end, never materialized. By 1966, the fate of the Valkyrie as a combat aircraft was sealed. No production order would ever come, and the bomber would never be stationed on alert with nuclear weapons. Instead, the two prototypes remained confined to Edwards Air Force Base and Wright-Patterson, serving as flying laboratories. Their role had shifted irreversibly, not as weapons of war, but as platforms to push the boundaries of aviation science. By the mid-1960s, the XB-70's role had shifted decisively from a potential frontline bomber to a research and test aircraft, but its story was far from over. Though it never carried weapons into combat, the Valkyrie entered an era of operational trials and experimental use that revealed both its technological promise and its inherent limitations. The aircraft became a flying laboratory, providing data critical not only to bomber development, but also to the future of supersonic transport and advanced aeronautics. The Air Force and NASA partnered in using the Valkyrie to study the effects of sustained Mach 3 flight. Each sortie tested structural integrity, materials resilience, and aerodynamic performance under extreme stress. Engineers focused particularly on the heating effects of high-speed flight. The XB-70's surface temperatures soared to levels that distorted panels and required constant inspection after each mission. Pilots reported that the aircraft handled remarkably smoothly at supersonic speeds, but behind the scenes, maintenance crews struggled with warped skin sections, leaking fuel lines, and overheating hydraulic systems. The Valkyrie could achieve its design goals, yet doing so exacted a toll that made operational deployment unrealistic. Combat adaptation, as originally envisioned, never materialized. Instead of rehearsing nuclear strike profiles, the XB-70 was tasked with experimental research. Its immense size and power allowed engineers to test aerodynamic theories that would later influence projects such as the Concorde and the Soviet Tu-144 supersonic airliners. Wingtip droop, compression lift, and high-speed shockwave interactions were studied in ways that no wind tunnel could replicate. The Valkyrie thus contributed more to science than to strategy, shifting from symbol of strategic dominance to instrument of technological exploration. However, the program's experimental phase was also marred by tragedy. On 8 June 1966, a publicity flight ended in catastrophe. North American Aviation arranged a formation flight of advanced aircraft for promotional photographs, featuring the XB-70 alongside an F-4 Phantom, F-104 Starfighter, T-38 Talon, and F-5 Freedom Fighter. During the maneuver, the F-104, flown by test pilot Joe Walker, collided with the Valkyrie's right wingtip. The impact tore the Starfighter apart instantly and severely damaged the XB-70, forcing it into an uncontrollable roll. Despite desperate efforts by pilot Al White to regain control, the aircraft disintegrated in the air and crashed into the desert. Co-pilot Carl Cross was killed, as was Walker in the F-104. Only White survived, ejecting at the last moment though badly injured. The accident underscored the hazards of flying such an immense and complex machine at the edge of the performance envelope. It also reduced the Valkyrie fleet from 2 aircraft to a single surviving prototype. The loss of XB-70A2 curtailed the scale of research missions and dealt a symbolic blow to the program. What had once been envisioned as a fleet of 100 bombers was now reduced to a single aircraft kept alive for experimental purposes. Despite the setback, the remaining XB-70 continued to fly until 1969, conducting research flights at Edwards Air Force Base. Missions focused on high-speed aerodynamics, sonic boom effects, and flight control studies. NASA, increasingly interested in supersonic transport, used the Valkyrie as a test platform for data that would inform civil aviation projects. In this capacity, the bomber found a second life, no longer a weapon of war, but a bridge to new frontiers in aerospace. From a combat perspective, the XB-70 never fulfilled its promise. It was never deployed to squadrons, never stood nuclear alert, and never tested in actual warfighting scenarios. Its combat adaptation remained theoretical, an unrealized vision overtaken by rapid changes in strategy and technology. Yet, in its limited role as a flying research machine, the Valkyrie's legacy began to crystallize. The lessons drawn from its failures and breakthroughs alike shaped the trajectory of American aerospace design in ways that would resonate far beyond its short service life. The Valkyrie's transformation from an intended nuclear bomber to an experimental platform meant that most of its development in the later years focused on variants, modifications, and technological spin-offs rather than operational upgrades. Originally, the Air Force had envisioned several specialized versions of the B-70 beyond the baseline strategic bomber: reconnaissance platforms, long-range strike aircraft with conventional payloads, and even air-to-surface missile carriers. These variants never advanced beyond the drawing board, as the shift in U.S. defense priorities undercut the rationale for a production fleet. Still, the ideas reveal how ambitious the program once was. North American Aviation studied designs for the RB-70, a reconnaissance model equipped with advanced cameras and sensors to penetrate Soviet airspace at Mach 3 speeds. Theoretically, this aircraft would have been immune to interception during the early 1960s, offering unmatched intelligence-gathering capabilities. Another proposal, the B-70C, envisioned a refined production model with structural improvements and more efficient systems based on the lessons of the prototypes. Discussions also considered a strike variant with a reduced crew and space for larger payload bays, optimized for standoff missile delivery. None of these designs advanced, as by the time the prototypes flew, The Air Force and Department of Defense had already withdrawn support for full-scale production. The two XB-70A aircraft that did exist underwent numerous modifications during their test careers. The first prototype, XB-70A1, was primarily used to validate aerodynamic principles. Engineers fitted it with different sensor packages, reinforced structural sections, and refined the wingtip droop mechanisms. The second prototype, XB-70A2, incorporated design improvements such as stronger materials, advanced instrumentation, and provisions for extended high-speed flight. Unfortunately, this second aircraft was lost in the 1966 collision, leaving only the first prototype to carry the program forward. NASA's involvement added new layers of modification. As the Valkyrie shifted toward research, the surviving aircraft was fitted with specialized test equipment for data collection. High-speed pressure sensors, temperature probes, and recording systems filled its bays, transforming it from a bomber into a flying laboratory. Experiments included studies of sonic boom propagation, which were of great interest for the future of civilian supersonic transports. Engineers also investigated airflow dynamics around the massive delta wing and fuselage, data that proved invaluable for later programs like the Concorde, Tu-144, and eventually the American SST project that never came to fruition. Another area of technological evolution influenced by the XB-70 was materials science. The stainless steel honeycomb structure, though difficult to manufacture, pushed aerospace metallurgy forward. Techniques developed for the Valkyrie informed later high-speed aircraft, including the SR-71 Blackbird, which relied heavily on titanium. While the Blackbird and Valkyrie differed in mission and design, both embodied the transition from traditional aluminum to advanced heat-resistant alloys required for supersonic endurance. Although no true operational variants of the Valkyrie were ever built, its influence extended across aerospace disciplines. Concepts tested on the XB-70 reappeared in various guises in other aircraft. The idea of using compression lift and movable surfaces to exploit shockwaves influenced later supersonic designs. Lessons from its high-temperature systems fed into rocket and spacecraft engineering, including thermal protection for re-entry vehicles. Even the avionics testing conducted on the Valkyrie provided insights into managing electronic systems in extreme environments. By the late 1960s, it was clear that the Valkyrie would never spawn the family of operational bombers once imagined. Yet in a different sense, it did give rise to a broad range of technological descendants. The aircraft had become a cornerstone in the lineage of supersonic research, shaping both military and civilian projects. Its modifications and adaptations reflected not a combat role, but a pivot toward science, one that ensured its legacy survived even as its original purpose faded. The XB-70's global impact and legacy lie not in the numbers built or missions flown, but in the influence it exerted on strategy, technology, and culture during and after the Cold War. Although it never became the operational bomber that Strategic Air Command had envisioned, the Valkyrie served as a symbol of technological ambition and strategic uncertainty, shaping both American aerospace development and the responses of other nations. Internationally, the Valkyrie was perceived as a potential game-changer. Intelligence reports reaching the Soviet Union in the late 1950s and early 1960s described a Mach 3 bomber with intercontinental range, capable of delivering nuclear weapons beyond the reach of any existing defense. Soviet planners, already burdened with the task of countering the B-52 fleet, now faced the possibility of an aircraft that seemed nearly untouchable. The accelerated development of advanced surface-to-air missiles and high-performance interceptors such as the MiG-25 Foxbat was driven in part by the perceived threat of the XB-70. Ironically, the Foxbat became operational just as the Valkyrie program was winding down, a testament to how anticipation of the bomber influenced global weapons development even without full production. In the United States, the Valkyrie's cancellation became an early sign of the Pentagon's shift toward missile-based deterrence and multi-purpose aircraft. The B-70 was effectively supplanted by the combination of ICBMs, submarine-launched ballistic missiles, and versatile bombers like the B-52 and later the B-1. Yet within the aerospace community, the Valkyrie left a deeper technical legacy. The data it provided on supersonic flight at extreme speeds and altitudes directly influenced the development of civilian supersonic transports. Both the Anglo-French Concorde and the Soviet Tu-144 benefited from research drawn from the XB-70's flights, particularly in areas such as delta wing aerodynamics, thermal expansion, and sonic boom effects. Domestically, the Valkyrie became a subject of public fascination. Its striking appearance, with long nose, canards, and vast wings, made it an icon of futuristic aviation. It appeared in aviation magazines, promotional films, and even toy models, capturing the imagination of a public accustomed to rapid technological progress in the jet age. To many, the Valkyrie embodied the idea that there were no limits to what American engineering could achieve, even if strategic reality ultimately limited its practical value. In cultural memory, the XB-70 also came to represent the risks of overreaching in weapons development. Its enormous cost, technical difficulties, and sudden obsolescence provided critics with a cautionary tale about the dangers of pursuing prestige projects without clear long-term utility. The nickname America's Flying Flop, though unfair to its genuine achievements, reflected the perception that the Valkyrie was a magnificent but impractical machine. This duality, marvel of engineering yet strategic misstep, has shaped its legacy ever since. The surviving prototype, XB-70A1, was retired in 1969 after completing its final research flights. It was delivered to the National Museum of the United States Air Force at Wright-Patterson Air Force Base in Ohio, where it remains on display. Preserved in pristine condition, it stands today as both a monument to ambition and a reminder of the shifting tides of strategy during the Cold War. Visitors are struck not only by its sheer size, but also by the audacity of its design, a tangible reminder of an era when speed and altitude seemed to offer ultimate security. In retrospect, the XB-70's greatest contribution was not in deterring adversaries or delivering weapons, but in advancing the science of flight. It bridged the gap between military necessity and aerospace exploration, influencing projects far beyond its original scope. Its presence in museums, textbooks, and historical documentaries ensures that its legacy endures, not as the bomber that never was, but as an enduring symbol of both the promise and pitfalls of Cold War aviation. Beyond its public story of canceled production and experimental research, the XB-70 Valkyrie possessed a series of lesser-known chapters that added nuance to its history. Some of these involved classified evaluations, others reflected ideas that never left the drawing board, and still others came from the reflections of the men who flew it. Together, they reveal how the Valkyrie, even as a technological orphan, continued to shape thought and imagination long after its brief test career ended. One of the more obscure aspects of the program concerned proposals to repurpose the Valkyrie as a launch platform for air-launched ballistic missiles or space research vehicles. Engineers in the early 1960s explored whether the XB-70's vast size and high-speed capabilities could make it a carrier for experimental weapons or even small satellites. Concepts included mounting air-launched ICBMs beneath its fuselage, releasing them at altitude to extend their range. These studies paralleled similar projects involving the B-52, though none were ever carried out with the Valkyrie. Budget pressures and changing priorities ensured such ideas remained speculative, but they illustrate how aerospace planners looked for secondary uses once doubts about the bomber role emerged. Another largely forgotten mission of the XB-70 was its role in sonic boom research. Public concern over noise pollution from supersonic flight became a significant issue during the 1960s, especially as civil supersonic transport projects gained traction. The Valkyrie's size and speed made it an ideal test subject for measuring and modeling sonic boom patterns. Flying over both military ranges and civilian monitoring stations, the aircraft provided invaluable data on the intensity, duration, and environmental impact of shockwaves. This research shaped not only the Concorde and Tu-144, but also later studies on mitigating sonic boom effects for future high-speed transports. In this sense, the Valkyrie's legacy extended directly into civil aviation policy and engineering. There were also whispers of classified defense evaluations. Though officially the XB-70 never carried weapons, some accounts suggest that the Air Force considered limited tests of nuclear delivery profiles, at least in simulation. Flight plans mirrored potential strike routes across polar approaches, and navigational systems were evaluated for long-range accuracy at supersonic speeds. While no confirmed weapons tests occurred, these operational-style flights indicated that the Air Force never entirely abandoned the idea of using the Valkyrie if geopolitical conditions shifted suddenly. The test pilots who flew the Valkyrie offered personal insights that rarely appeared in official reports. Al White, who survived the 1966 crash, often remarked on the aircraft's remarkable stability at Mach 3, describing it as like flying a giant arrow through the sky. Joe Cotton recalled the immense psychological impact of looking down at the curvature of the Earth from 70,000 feet, while knowing that the machine beneath him was operating at the edge of material science. Their reflections highlight the sense of awe that accompanied the XB-70, even as it remained bound by strategic irrelevance. In later years, declassified documents revealed how close the program came to complete termination much earlier. At several points between 1961 and 1963, the Valkyrie was within days of cancellation, saved only by political maneuvering and Air Force lobbying. These reprieves allowed it to fly and generate its historic research data, but they also underscore how precarious its existence was. Had budgets or political winds shifted slightly differently, the XB-70 might have remained a paper project, remembered only as an ambitious sketch rather than a tangible aircraft. Today, the XB-70's unseen chapters add depth to its reputation. It was not merely a flop, but a versatile tool pressed into scientific roles far beyond its original intent. It tested sonic booms for civil airliners, carried instrumentation for NASA, and expanded knowledge of flight at speeds and altitudes where few other aircraft could operate. Its pilots remembered it with pride despite tragedy, and its engineers pointed to it as proof that even the most challenging designs could be brought to life. Thus, the Valkyrie's forgotten missions and hidden stories reinforce its paradoxical legacy. It was an aircraft conceived as a weapon, but remembered as a research icon. Its operational history was truncated, yet its contributions to science, engineering, and even cultural imagination remain vivid. By examining these overlooked dimensions, the XB-70 emerges not simply as America's flying flop, but as a pivotal chapter in the broader story of Cold War aviation and technological ambition. The conclusion of the Valkyrie's story unfolded not in the roar of engines at Mach 3, but in the quiet halls of research laboratories, congressional hearings, and museums. By 1969, the sole surviving XB-70 had completed its final flights, closing a chapter that had begun with visions of a fleet of more than 100 nuclear bombers and ended with just one aircraft preserved as a technological monument. This ending reflected not only the fate of a single program, but also a broader transition in American strategic doctrine and aerospace priorities. As intercontinental ballistic missiles became the backbone of U.S. nuclear deterrence, the rationale for high-speed bombers diminished sharply. Submarine-launched ballistic missiles provided a second secure leg of the nuclear triad, leaving manned bombers to occupy a more flexible but secondary role. In this environment, a massively expensive, technologically complex Mach 3 bomber no longer fit strategic needs. The B-52 Stratofortress, though subsonic and already aging, remained far more economical and adaptable, and it continued to serve for decades while the Valkyrie faded into history. Politically, the XB-70 became a touchstone in debates about defense spending. Supporters of Secretary of Defense Robert McNamara pointed to it as evidence of unnecessary excess in Cold War weapons development, an aircraft rendered obsolete before it even entered service. Critics countered that its cancellation represented a loss of American technological edge, arguing that adversaries like the Soviet Union were pushing ahead with advanced interceptors and missile systems precisely because they believed the Valkyrie would be built. The truth lay somewhere in between. The Valkyrie had indeed spurred adversary developments, but its costs and vulnerabilities made its large-scale deployment unrealistic. Technologically, the aircraft's influence continued long after its last flight. Lessons learned from its stainless steel honeycomb construction informed later approaches to high-speed and high-temperature materials. Data on compression lift, shockwave interactions, and supersonic control systems fed into both military and civilian aerospace projects. Even though the American supersonic transport program was eventually canceled, its research drew heavily on the Valkyrie's data, as did NASA's later work on high-speed flight. In this sense, the XB-70 contributed indirectly to shaping the scientific knowledge that underpinned projects ranging from supersonic reconnaissance aircraft to experimental spacecraft. Culturally, the Valkyrie retained a mystique that outlasted its operational relevance. For aviation enthusiasts, it represented the zenith of Cold War ambition, a machine that pushed the boundaries of speed, altitude, and engineering audacity. To critics, it remained a symbol of waste and overreach, yet both perspectives underscored the aircraft's enduring symbolic power. Unlike many canceled projects, the XB-70 continued to fascinate because it had flown, it had been real, and it had achieved what it set out to do in technical terms, even if strategy moved past it. The preserved XB-70 at the National Museum of the United States Air Force stands today as the ultimate expression of this paradox. Visitors are struck not only by its sheer scale, but also by its elegance, the sleek white shape that seemed decades ahead of its time. In the museum context, it is no longer judged as a failed bomber, but celebrated as an extraordinary research platform and a feat of design. It embodies both the promise and peril of Cold War innovation, proof of what could be achieved when cost was no object, and a reminder that technological brilliance does not always equate to strategic utility. In the end, the Valkyrie's legacy was to mark the twilight of the era, when speed and altitude alone promised invulnerability. The shift toward stealth, precision, and missile deterrence defined the decades that followed. While the lessons of the XB-70 inform those new paths, it remains one of aviation's most striking contradictions. A bomber without a war role, a project without a future, yet an aircraft whose contributions to knowledge and imagination secured it a place among the icons of aerospace history. Even after its retirement, the XB-70 Valkyrie continued to influence aerospace research in ways that were not widely recognized at the time. Much of this came through the classified or technical programs that relied on data generated during its relatively short flying career. Engineers and scientists drew upon these results for decades, and in certain circles, the Valkyrie was remembered not as a failed bomber, but as an invaluable testbed that answered questions no other aircraft could. One of the key areas where the Valkyrie contributed was in high-speed structural dynamics. Researchers had struggled to understand how large, flexible airframes behaved at sustained supersonic speeds. Smaller fighters like the F-104 or even the SR-71 operated under different loads and scales. The XB-70, with its enormous wings and mass, gave engineers insights into aeroelasticity, how structures bend and twist under aerodynamic pressure at Mach 3. The data informed not only bomber and transport projects, but also influenced designs in the emerging field of reusable space vehicles. Understanding how materials expanded, contracted, and stressed under continuous heating cycles fed directly into later thermal protection concepts for spacecraft. Another field shaped by the Valkyrie was propulsion integration. The YJ-93 engines, with their complex intake and exhaust systems, became a case study in how to manage airflows at extreme speeds. Engineers analyzed compressor stalls, thermal stresses, and fuel efficiency under conditions few other platforms could replicate. These lessons proved useful in the design of hypersonic research vehicles decades later, as well as in refining supersonic combustion theories. In many ways, the Valkyrie offered a bridge between jet-age propulsion and the experimental ideas that would later drive projects like scramjets and spaceplanes. There were also overlooked contributions to environmental and atmospheric science. During its high-altitude flights, the Valkyrie carried instruments that gathered data on the stratosphere. These flights provided measurements of temperature, pressure, and airflow at levels rarely visited by aircraft. In some respects, it acted as a precursor to high-speed environmental research platforms. Although its primary mission was never scientific in the academic sense, the data proved valuable to researchers studying the upper atmosphere, sonic boom propagation, and high-altitude weather patterns. From the perspective of the men who flew and maintained it, the Valkyrie was remembered as both a privilege and a burden. Test pilots often described it as awe-inspiring to handle, yet they acknowledged the constant tension of flying a machine that was, in many respects, experimental each time it left the ground. Ground crews wrestled with the maintenance challenges of its exotic materials and fragile systems. Their recollections highlighted the paradox of the Valkyrie. It was both a marvel of engineering and an impractical machine, too complex and costly to operate on a wide scale. Internationally, the XB-70's legend continued to reverberate. In the Soviet Union, rumors persisted that the United States had hidden an operational fleet of Valkyries ready to be deployed in wartime. Western analysts sometimes noted how Soviet interceptors and air defense systems of the late 1960s and 1970s seemed to be designed with a phantom threat in mind, the possibility that more XB-70s existed than acknowledged. Though false, these perceptions show how the aircraft retained psychological weight even after its cancellation. In cultural memory, the Valkyrie found a second life in documentaries, books, and exhibitions. Aviation writers often return to it as a symbol of Cold War ambition, highlighting both its successes and its shortcomings. Model kits, paintings, and popular articles kept it alive in the public imagination, often portraying it as a futuristic machine ahead of its time. While some emphasized its nickname Flying Flop, others celebrated it as an icon of engineering daring, a machine that, despite strategic irrelevance, represented the very peak of American aerospace capability in its era. By the time the Valkyrie era closed, its role in history had become more complex than its original mission. It was neither simply a failure nor purely a success. It was a hybrid, an aircraft that failed as a weapon but succeeded as a research tool, a platform that justified its existence not in the missions it flew, but in the knowledge it left behind. This duality defined its place in the narrative of Cold War aviation, ensuring that the Valkyrie would never be forgotten, even if it never fulfilled the destiny once written for it. The story of the XB-70 Valkyrie ends as one of the most striking paradoxes in the history of military aviation. Conceived as a weapon of unmatched power, it was meant to fly faster and higher than any adversary could hope to counter, carrying America's nuclear arsenal deep into Soviet territory. In that vision, it embodied the optimism of technological supremacy that dominated Cold War thinking during the 1950s. Yet by the time it flew, the strategic logic underpinning its existence had already dissolved. Intercontinental ballistic missiles and submarine-launched missiles made the role of a Mach 3 bomber obsolete, and advances in Soviet air defense ensured that speed and altitude alone no longer guaranteed invulnerability. The Valkyrie was canceled as a frontline bomber before it ever entered squadron service, its fleet reduced from more than 100 aircraft on paper to just 2 flying prototypes. One was lost in a tragic accident that underscored the risks of pushing the limits of aerospace engineering, leaving only a single airframe to carry out research flights. For critics, this was proof that the project had been a costly miscalculation, a glamorous machine with no practical purpose. The label, America's Flying Flop, reflected that frustration, reducing it to a cautionary tale about excess in defense spending. But history has given the XB-70 a more complex legacy. As a research platform, it advanced understanding of supersonic flight in ways that no other aircraft could. It provided data on materials science, high-speed aerodynamics, and propulsion integration that influenced both military and civilian aerospace projects. Its contribution to sonic boom research shaped debates on supersonic transport, while its lessons on high-temperature structures informed later high-performance aircraft and even aspects of spacecraft design. Though it never delivered a weapon, it delivered knowledge, arguably a more enduring contribution. Culturally, the Valkyrie became an icon of ambition. Its futuristic silhouette, enormous size, and ability to cruise at Mach 3 captured the imagination of engineers, pilots, and the public alike. Preserved today at the National Museum of the United States Air Force, the surviving prototype stands as a monument not to failure, but to aspiration. Visitors are struck by its presence, by the audacity of its design, and by what it represents about the era that produced it. A time when technological limits were tested relentlessly, even when strategic utility was uncertain. The Valkyrie's place in aviation history is therefore not defined by its absence from combat or its cancellation as a weapon system. Instead, it is defined by the boundary it marked between 2 eras. It was the last of the high-speed, high-altitude bombers built on the belief that sheer performance could ensure survival. In its wake came stealth, precision, and a reliance on missiles, doctrines shaped by the very vulnerabilities the Valkyrie revealed. In this sense, it closed one chapter of strategic aviation while opening another. Ultimately, the XB-70 was neither a triumph nor a waste, but something in between, a technological masterpiece trapped by shifting strategic realities. Its story is a reminder that innovation often moves faster than doctrine, and that some machines achieve greatness not on the battlefield but in the knowledge they leave behind. the Valkyrie's legacy endures as a testament to the ambition and audacity of Cold War aerospace, and is one of the most extraordinary aircraft ever built, regardless of the mission it never flew.